About 7 o'clock. Looks like we can get going. Welcome back, everyone. I'd say the most exciting announcement is not quite that we're on the last problems of this section, but that is pretty exciting on its own. But also, all exams have now been returned. So I haven't updated this yet since I haven't graded the makeup exam, but I don't expect that to move too much. And the fall 2024 exam 2 solutions are also posted down here as well if you would like to check them out. One thing I do want to mention is I think we mentioned this before, but you always get two scores, and that's kind of confusing because your exam score is a fraction converted into a percentage, and your course score is just your grade, now including both exam 1, exam 2, as well as all the homeworks. And the way I graded this was I graded up till everything that was due, everything that was handed in, I believe on, that must have been either Saturday or Sunday, I'm not too sure. But after that, I put everything together with your course score. So if you turned in other problems and stuff like that, your course grade might change a little bit up here, but it's a good idea to keep checking this, say at least weekly, just to make sure nothing's missing, everything looks correct. Well, any questions at all, folks, that we'd like to discuss on the exam? Let me pass one back while we're thinking that over. It's a weird spot to leave the middle screen on. Let me put it back down to here. There we go. That's a little bit better. Well, for folks in the in-person section, I do have your hard copy, so I think everyone in class has already gotten theirs. But if you don't get yours back, but you're in the in-person section, you're also welcome to just email me, and I have no trouble just scanning them and emailing them back to you. Also, for folks in the fully online section, the folks out here in Zoom, I emailed you back your exam. Everyone except for the one student that had a makeup exam, of course, I still haven't graded that one. But for everyone else, I just went to your ISU email and emailed you back your exam. If you're missing any exams, just let me know at any point. I have no trouble re-emailing those. Well, any questions at all, folks, before we get started with today's work? Okay, well, we're actually getting pretty far into chapter 11 at this point. Once we cross past section 11.4 and get into 11.5, it has the alternating series test. It also has the test for absolute convergence. That's when we have just about every test on the complete list here for the summary of tests. Only things that are missing are going to be ratio tests, root tests, and other things along those lines, but really not too much. So we're making really good headway through chapter 11. But once we get into, say, 11.6, 11.7, and so on, the sections 11.1 through 11.5 become extremely important. It's a lot of different tests, and the more you can study those and get a feel for how they go, the easier the rest of chapter 11 is. If section 11.1 through 11.5 is a little foggy, that's kind of normal. We're learning it for the first time. But if we have that same kind of feeling when we're all the way, say, section 11.10, Taylor series, Maclaurin series, it makes that section just almost unapproachable unless we really have a good feel for these sections. So the faster you do the homework, the easier it is, because these ideas, again, they have a shelf life. After class, the longer it goes before you look at that information again and try those problems, the harder it gets. So I realize everyone has pretty busy schedules, but the best thing to try to do is work on them the moment you get available time. Try to find a steady routine to get in a habit of doing the homework, and it'll make all the difference on exams. In fact, that's why homework is worth 30% in this class, because it's not easy, it's tedious, but if you can get through the homework, you are studying for the exam questions. But after that spiel, let's take a look at what we left off in section 11.4. We were dealing with the limit comparison test, which is a pretty fantastic test. And I have to admit, when you start to get the hand of how this goes, it almost feels like this test is not a big deal as much, but I would understand if you don't use the comparison test as often and you use the limit comparison test way more, but always think about this comparison test. The reason it exists is because there are just certain problems that suddenly that's the test you absolutely want to use, even though limit comparison test is sometimes more applicable. But after that spiel, let's try this out. I think we mentioned before leaving class on Monday that this is one of those series where you could stare at it for a long time and not have too many good ideas on how to even approach it. So this is one of those kinds of series. I would never throw this on a real exam without a hint, try this test. So we're not trying to put down confusing problems on these all the time. But the hint on this one is definitely it is a limit comparison test. If that's the case, we have to find something to compare it to. And that's going to be a new series, Bn. So we'll begin by saying let summation Bn, this is the way we indicate the symbol and the name for the new series. More definitely, it goes from 1 to infinity. And things to try are hard to come up with this on this one. Any volunteers for something to try? It turns out, if you're not sure, that the thing that actually works on this, and I don't know who would have guessed this by looking at it just for a few moments, but what actually works is this thing. The good old harmonic series makes its way into this problem out of nowhere. Maybe there's a hint there. 1 over n being inside the sine function suggests that could be something to try. So we need to test this thing. You could use the p-series test, but the one time you can get away with that is if you just know the name of this series. This is the harmonic series known to diverge. So if this is a series with a name and it's a foregone conclusion, whether it converges or diverges, you can just state that rather than running through a whole test. So we have a divergent harmonic series. In the limit comparison test, we take this thing. Let's give this one a name, summation an. And we're going to form this limit right here by the red dot. We'll take the limit as n goes to infinity. Let me get that red dot to settle. Of the series an divided by Bn. So now we have this limit as n goes off to infinity. First, we've got for the series summation an sine 1 over n and the numerator. Then it's being divided by Bn, which is 1 over n. And that's our limit we have to resolve. Actually, it's not too bad of a limit. And depending on who you took Calculus 1 from, you might recognize this from the L'Hopital section all the way back at, I think, 4.4 or something. I think this is an actual problem. Instead of sine, it might have been cosine. So the idea with this one is, it is a L'Hopital rule problem because as n goes to infinity, 1 over n goes to 0. So we have sine of 0 in the numerator, which is 0, being divided by, well, as n goes to infinity down below, 1 over n also goes to 0. And so this is indeterminate. That means we get to use L'Hopital's rule on this problem. And we did have a little bit of a discussion on this. When we go to use L'Hopital's rule, we write this out. The superscript h above equality is not required, but it's just an indication this is a different kind of step. We're taking the limit still as n goes to infinity, and we differentiate this function. Derivative of sine becomes cosine, 1 over n, and then we multiply by the derivative of 1 over n through the chain rule. But notice how weird that might seem already. The sequence sine 1 over n is not a continuous function. You can't differentiate this. So the refresher on why this really works out is, let's just put a little pause right here, because I think this is confusing enough to take a look at the second time. We go to one particular theorem that makes this suddenly a logical problem make a little bit more sense. And somewhere in these notes, there's a theorem. Let me find it. I think it's at the top. Yeah, it's this one right here, theorem number 3. It says if the limit of your function is L, and the limit of the sequence comes out as L, then if your function is defined to take on the values that the sequence gives at integer values, you have the same exact limit here as you do here. So in other words, even if we defined a continuous function for which you can differentiate, continuous and differentiate, take the limit in this way using L'Hopital's rule, you get the same conclusion whether you used the terms of the sequence rather than a new function x. So essentially what theorem 3 allows us to do is abuse the notation a little bit more. Let me move that comment over and use L'Hopital's rule without actually having to define f of x. If you decide to define it first, no harm done. I'd say that that's being really careful with notation, and it's a good call. But it's not too uncommon to see this in the reading, where we differentiate something that doesn't even look like it's differentiable in the first place. It's just through the use of that theorem. So back on track, that's the derivative of the numerator. And then down below, in L'Hopital's rule, you take the derivative of the denominator. But this is one of those weird times where you might have noticed with the setup on the chain rule, maybe you don't want to fully differentiate it. Just put the prime symbol on it to make it correct. Because now that cancels. It's not as if we can't calculate it. It's -1 over n squared. But why bother? It's just gone right at that step. So we're now taking the limit as n goes to infinity of cosine 1 over n. As n goes to infinity, this turns into cosine 0. That's a little bit of a problem because recall, our limit has to come out as some constant c that's finite and positive. So if I had sine 0 right there, the entire limit comparison test has failed because sine of 0 is 0. So lucky we have cosine 0, which is 1 greater than 0. So the limit is finite and positive. And now we can say our conclusion. Both series either converge or diverge. Because we used a comparison on a divergent series, both of them, this one included now, has to diverge by limit comparison. So that's our conclusion. We'll say, therefore, summation an, just to be specific, let's write it out. This feels more impactful as a conclusion. Summation as we go from 1 to infinity of sine 1 over n, it must diverge by limit comparison. So for the instructions, we have to give a conclusion. We have to show the steps, like writing out the limit, showing the steps there. We have to indicate the test we used. You might say by the limit comparison test, but if you shorten these up, that's okay as well. As long as I know what test you used, as long as I know that you know what test you used, that's okay to put in some shorthands there. But we did it, folks. That's the limit comparison test on a series that, this is one where someone just randomly gave it to me on the street and said, does it converge or diverge? I'd have no idea, know where to get started, because this one takes ingenuity and creativity to even come up with what you're comparing it to. But again, the 1 over n right here, I think that's the biggest hint. Well, this is our complete section on the comparison test and the limit comparison test. What we're going to do next on the problem down below is do a synthesis kind of problem, looking at all the tests so far, and see if we can pick out which test matches up with which. But any questions or comments at all, folks, on this one? Okay, as we get more and more tests, these kinds of problems become extremely important. We always have to constantly remind ourselves, what are the tests? What are the series that apply to those kinds of tests? And which way do you make your conclusions? So this is really just one step in going in that direction. We're going to match test 1 through 6 for convergence divergence with the correct series for which it'll apply. And we're trying to do something even more. We're going to match each test with exactly one series and then stop. Don't fully test the series. Not because we don't have to. So if we want to solve a couple of them, that's okay. Just let me know. I wrote these instructions as if it's a real exam question, essentially. So for a real potential exam 3 question or final exam question, sometimes the problems look like this, where you're not doing the whole process. It's more of a kind of an organization type of problem. First on the list is test for divergence. And because we're trying to understand these tests better, let's just pull up those tests so we can get a good feel for each one of them as they come up. A good document could be summary of tests for series, this one right here. This is the one I'm going to use a little bit more because I'm trying to match up the actual notation our author uses. There's small differences in notations on this one, convergence, divergence, flowchart. But I left it on here just in case if this is a good way to organize information in your mind, it's still a great document. But I'll traditionally use this more often than not. So first test listed here is the test for divergence. Let me just get this window going a little bit better. The test for divergence says if the limit of the nth term of the series doesn't exist, or if it's non-zero, 5, -2, anything like that, then the series diverges. So for this test up here, anyone see the right series for which that test is going to work? You could say row 1, series 2, row 3, series 3, something like that. You know, it would help if I just numbered them. That would help too. So numbers 1 through 6. Test for divergence works on exactly one of them. Yeah, go ahead. Let's see. It wouldn't be 4 because the problem with 4 is if we take the limit as n goes to infinity on 1 over n cubed minus 8, we'd get a value of 0 in that limit. And with the summary for tests, in the test for divergence, we have to get a non-zero value or it does not exist to apply and get the conclusion of divergence. So this one doesn't work for test for divergence, but you know what? That's okay. We can think of this as elimination as well. That's good information. Any other volunteers for another one to try?
Is it question 5?
Good call, absolutely, Kaylee. On this one right here, if you take a look at the form of the nth term of that series, the 2n and the 3n is the giveaway that this one should work with test for divergence. We're not necessarily doing the test, but we ought to do it for this one. Let's say for 5, use test for divergence. Div is a good shorthand for that one. So I'll say that this one matches up with series 5. Or actually, that might be a little bit too much information to put on there. Test for divergence works really well because the limit of that, as you go from to infinity, of 2 to the n, 3 to the n minus 1 is 2/3. That's because the degree in the numerator, denominator are exactly the same, so we just grab the coefficients. That's not 0, and so if we run this whole test, it tells us the series diverges. So one test down. Next, we need to find a geometric series. Or if another one just pops out at you, if you find the one that looks like the P series or the one for limit comparison, let me know. But if we're going in order, anyone spot a geometric series in that list?
That'd be number 2.
Absolutely, good call, Christopher. What makes this one geometric series and the giveaway on it is the fact that the exponent n, or excuse me, the index n is written in as an exponent. That alone makes it a geometric series. That's right here. Geo series is a great shorthand for that test. And if you go geo dot s dot, that's enough for me to say you are indicating geometric series test. But I'll write out just a little bit more for the notes. Instructions said not to test them, but you know, honestly, it's kind of tempting. This is a better review problem if we do some of these fast tests. The geometric series test says you have to have something of that format. It just so happens our R is a total fraction, so it looks a little bit more confusing to look at versus this form up here. We have convergence if, let me move that over, R is less than 1. We're not worried about the total sum unless we're asked to calculate it. An exam question would have to directly say, and find its total sum. So we'll say on this one, R equals -1/7, which would imply absolute value of R is less than 1. And this one does converge. So 2 down, we've got test for divergence and the geometric series down. The next easiest test to apply and use, I'd say, would be P series after those two. Anyone see where the P series is in this list? You know what? It's really close on 4, but 4 would require a comparison test. So if we compare this to a p-series, we could make that work. I missed that the first time I was looking through because these exponents, they're just kind of all over the place. But that is the one right up here. Let's just blow it up a little bit. This one's the p-series. And let's just say that here to start. We need to use a p-series test on that thing. Take a look at our summary. P-series is great, but you've got to get it in the right format. You need to consolidate base n into the denominator to exhibit the exponent, and then just look at the sign. Convergence if it's strictly greater than 1, divergence in all other cases. So let's take a look at this one as well. If it's the cube root of n in the numerator, that's n power third. Divide by n, or you could say n power 3/3, which means we have 1 over n power 2/3. P is then 2/3, which is less than or equal to 1. And so this one is divergent as a p-series. So 3 down, and that means there's just 3 different series left over to take a look at. I think I kind of spilled the beans on 5 though, so I'll take this one. 4 is very close to being a p-series, but the thing that's really punishing on our tests here is that the form has to be matched exactly, and all it takes is a +1 or a -8 to throw it all off. But we did things like these at the very top of the notes. Say something like this one, for example. That one's not a p-series either, and neither is these, but if you use a comparison test, you can compare it to a p-series. So let's take a look at this again. If we're using this right here, I would say the best test is the comparison test. And you know what? It's not harmful to go through the motions to see if that's even right. This looks convergent as a p-series if the -8 was gone. That means when we go to estimate, we need less thans working out for us. Let's see if that would work. N cubed -8 is definitely less than n cubed. So now if we take the ratio of these, take the reciprocals of both sides, 1 over n cubed -8 is bigger than 1 over n cubed. And that looks like it's actually a big problem for us. That's a huge problem because this looks like it ought to converge, but the comparison test requires less than going in right there, not greater than. If I have a new series with terms greater than a known convergent one, it's unhelpful. I need my terms to be less than. So it looks like the comparison test actually does not work on that one. My bad. If the comparison test doesn't work, you go next to limit comparison test. That one, we will resolve it. So I take it back. These are harder to pick than I thought. This one is limit comparison. On a real exam question, I do try these out, and I would be tempted on a real exam question to go, okay, fixed, it's now comparison test, but that's cheating for us. So let's keep it the way it is. So if limit comparison works, then we have to compare to something that's similar. So summation Bn will be summation n goes from 1 to infinity. We'll keep the 1 in the numerator. The denominator will keep n cubed. That's the most dominant term when n is large. So for very large n, the series in black becomes highly similar to the one in blue. Now, we know this one converges. Dang it, that's a whole new test. We can say converges P series P equals 3, greater than 1 is the condition on convergence. And so that's all the work you have to show for testing this one in blue. But then you have to do a limit. So lim as n goes to infinity, you take this 1 over n cubed -8. You divide it by 1 over n cubed, which means you're multiplying by n cubed over 1. That exponent's impossible to read. Let me fix that one. Then when we go to take this limit, it's n cubed divided by n cubed -8. Let's just write it once more so it's slightly easier to visualize. That's a rational function in the variable h, and so it has a horizontal asymptote found by taking the coefficient 1 here, divide by the coefficient 1 here. In other words, the limit is 1, and in limit comparison tests, that means we were successful. That's greater than 0, and it tells us summation an, this one, either converges or diverges. It depends on what we said right here. We compared it to a convergent series, so an must converge. Well, we're actually doing all the tests, but you know what? It's a good review problem, so let's keep on going. Any questions at all, folks, with the comparison test on 4? Oh, right there. Yeah, it should be the same number. Thanks for spotting that. That's something that's like a huge blind spot for me. Sometimes, even if I write the problem, I sometimes think they're all going to be 1 where it starts. Looks like this one's starting at, you know what? Looking at that further, it ought to have started at 3, right? Because if it starts at 2, your very first term is undefined, 1 over 8 minus 8. So let's do a little bit more surgery on this thing. This one had to start at 3. We're going to have to fix that typo on the master notes later on, which means down below here. Thanks for spotting that again. This one has to start at 3. Let's get a pen that's going to pop out a little bit better. And thankfully, when we take limit as n goes to infinity, that's forgiving because we just shoot past any kind of issue like 3 as a starting point. But other questions or comments at the moment? Okay, thanks again for spotting that. You have a very good eye for subscripts. I need to practice that a little bit more myself. But let's keep on going through on the next ones. There's just 2 left. And we just used limit comparison test. So this one's off the table. Integral test is really touchy. Which one would you say works best for integral test? We might make it work on that one, but this one might be a better candidate. What makes this one a better candidate is if you're going to integrate, I'd say this is not too bad. It might require integration by parts. This one could be done, you'd integrate by a U substitution. If we're matching each test with exactly 1 series, I don't think we want to do 6 by a comparison test. You'd have to come up with something pretty phenomenal to compare that against, a pretty non-standard series, I'd say. Not saying the comparison test won't work. I'm just saying that might require loads of extra creativity to make it work. So it looks like integral test should go to this one on 6. Let's write down integral test. We kind of ran out of options, so we have shoehorned in comparison test on this one. So that's the full list. It looks like we got a good match and even a typo correction while we were at it. We didn't test 2 of these, so I'll leave it up to the class. Any further ones you'd like to take a look at or any further comments on this kind of problem? Okay, this one didn't work with the comparison test because of the -8 and the fact it converges. This one does work because of the plus. That's all that makes it work. And the fact that it's degree 4 in the denominator, degree 1 in the numerator. We'd compare it against 1 over n cubed potentially. So those are the last 2 tests we didn't take on. And from here on out, looks like we're pretty much done with section 11.4. Any last overall questions on the comparison tests folks would like to discuss? Okay, well, let's take this information and take a look at our new tests. Alternating series test is fantastic because you might have noticed something with our tests. I think I mentioned this a couple times too. When we talk about things like the comparison test, the limit comparison test, even the integral test, one thing that's been really common for all these tests are these statements. The function is always positive. That means if the function matches the index of the sequence right here, your series terms are always positive. Then even worse, comparison test says positive terms for both of those sequences. Your series can then only have positive terms. same exact condition on the limit comparison test. And so we might be wondering, what in the world are we going to do when there's actual negative terms? There are two strategies. There are negative terms in your problem and you want to eliminate them. The test for absolute convergence is a huge, huge tool. We just hit the terms of the series with absolute value and see what happens. But before that, here's the alternating series test. It says if you have negative signs, because it alternates positive, negative, this is a fantastic test to test your series. It's not like using the absolute convergence test, which could be a lot of steps. So let's take a look at that whole test formally. Well, I guess this is not the test. This is just the definition. We'll get to the test soon. But this is a good starting point because if you're going to use the alternating series test, you've got to know for what series in the first place does it even apply. So it says, if you can write a series like this one, just generically, into this form, where it's -1 to a power n. It doesn't have to be power n. It could be power n plus 1, power n minus 1, and so on. But this alone is what causes it to alternate. When n is 1, it's negative. When n is 2, it's positive. And so signs alternate for all time. And we can say that this whole thing, whether we put in the -1 to a power, is an alternating series. So specifically, that doesn't have to really be shown. You can have something like, say, cosine n times pi, and there's your +1, -1s. So watch out for that. Sometimes the fact that it's alternating could be hidden. With that in mind, what would y'all say with part A? Is that alternating or not alternating? Looks like some people are shaking their heads no, and I agree with folks. This is not an alternating series because what's missing is that you have to have a power around n to really make it oscillate or alternate. So we can say here on this one, this is not alternating. And I mean, that's the right answer, but you know what the best explanation is? Take the series written in summation form and just write it out. Plug in 1, you get -1. And it's not common. This is a series. These are being added together. Plug in 2, you get -1/2. Plug in 3, it's -1/3, and so on. And so if you just write out the terms of the series, you can plainly see, definitely it's not alternating. Sometimes that is the best strategy. Then when we go to this one's a bit of a problem. If we take a look at cosine n, and we actually write out the terms, we would get cosine 1 over 1 squared plus 3, so a 4, plus cosine 2 over 2 squared plus 3, so a 7, cosine 3, 3 squared plus 3, that's going to be 12, and so on. Well, this doesn't really resolve it at all, right? We need to calculate these values. I knew I was going to need a calculator, just forgot to load one. Let's take a look at cosine. So our terms are cosine 1, that's positive. Cosine 2, that's negative. Hey, that's already kind of promising. That means it's potentially oscillating, right? Cosine 3 is negative again. So right there, that's the problem. If you match up signs, negative, negative, it's already not alternating by that alone. So we can't use alternating series test on this one either. Kind of unfortunate. Let's say that's right here. So I believe it was this one and this one. These are negative terms. And so it is not alternating. Now for the last one, that's absolutely an alternating series. The telltale sign is this right here. So that's what you want to look for, something like that. It doesn't always tell us the full story. Sometimes, again, these can be disguised. But if we start plugging in values on this one, plug in 1 and we'll get 1 over e. Plug in 2 and we'll get -1 over e squared. For value 3 here, it's back to positive with the e cubed. Put in a 4, and we get a negative 1 over e power 4. And at this stage, I'm totally convinced, really as convinced right where it was yellow, but it doesn't hurt to just analyze the signs. Doesn't matter if it starts positive here, doesn't matter if it starts negative here. What matters is if you go from term to term to term, the signs will alternate. So this is an alternating series. Well, any questions, folks, on just categorizing these series as alternating or not? Okay, so now that we have all
Is
that,
it always alternating over y equals 0? Or can it be like alternating over a different asymptote sort of thing?
what do you mean by alternating over an asymptote?
I guess alternating asymptote is a bad word. No, could it be like alternating over um a different y value, or is it always alternating over y equals 0?
I'm not too sure what you're referring to with the y equals 0 on the problem.
Like it just keeps bouncing around like y equals 1, like going.
Oh, I see what you mean. So like as a graph like this, y equals 0.
Yeah, okay. So I see that in the book a lot. He uses some graphs to
Yeah, absolutely. So what would make a series like, say, this one alternating is, yes, it has to all bounce up and below that particular line 0. So it could be something wild like, say, this. This is enough to make it alternating, just as long as some terms are positive, some are negative, but they alternate in their sign like that. But it does have to be about a line y equals 0 for where they have to alternate their position on.
So like cosine of x plus 1 wouldn't.
It wouldn't, unfortunately. What we would need is something like, say, let's put both of these on. So if we had y equals cosine x, it's a bit of a problem because as you can see, if you're in the right spot here, some of these things are negative. Oh, that's 0. 1, 0. You know what? I need an index here. That's what would help out. Some of these things are positive. Say, you plug in a 1 here, it's a positive value. And if you plug in a 2, you're negative. But then if you plug in a 3, it's hard to hit, you're negative again. So that's what caused the problem. So at 2, it's negative. Down at 3, it's negative again. But you can fix this. You can throw in a pi on that thing. If you throw in pi, look what happens next. So that's at 0.5. At 1, we're negative. At 2, we're positive 1. At 3, we're at negative 1. At 4, we're at positive 1, and so on. So the right thing inside your cosine function will make it alternate. But if you put in something arbitrary and bizarre, like now divide by 2, this could be a problem. So it has to work out just right for that. But does that help with those questions about the alternating aspect of these? Okay, thanks for asking those questions. It's always good to visualize these in a different kind of way. So I appreciate that question. So with all of our series so far, alternating series, when they come up, this is the only one that came up, we need a good test for this kind of thing. And the test is this thing, the alternating series test. Now, what's kind of interesting about this test is when this test fails, test for divergence is the next natural choice. Not saying it's always going to be the test that resolves a problem, but if I use this alternating series test and I don't get, say, that condition to work out, then the whole test has failed. But test by divergence, more often than not, pretty much every problem in the homework set is going to work out for us to give a conclusion of divergence instead. So let's take a look at this really carefully. It says if the alternating series, and again, this is the part that makes it alternating, -1 to a power, satisfies two hypotheses. Hypothesis one, this part is decreasing. That part actually plays a very special role. This is the positive portion of the alternating series. Let's call this just the positive portion. Where we've factored out the -1 to a power, we're just looking at something positive, and that positive sequence here needs to be decreasing. And it has to be decreasing in a specific way with a limit of 0 altogether. If both these conditions apply, then the alternating series must converge. Well, any questions about that test so far, folks? Okay, well, here's our very first one for the day. And just for the sake of visualizing this a little bit better, to see how this could be plausible, let's do a little bit of extra visualization on this through Excel before we get started. Excel is never going to be the full answer to whether it converges or diverges, just for a way for us to try to get some extra intuition if we have some brand new test like this one. So we start with n, we put in an, and then we put in the partial sums Sn. Let's not put in too many. Let's say start at 1. An is then going to be equal to -1 to the power of the index. And then we divide by, oh, hang on. It's -1 to the power of the index minus 1. So it's got to look like that for the -1 portion. Then when we go to divide, we're just dividing by the index n. And that's our first term. Let's think about that. If we plug in 1, yeah, that's 1 over 1. Sn is going to be this value. Now if we go to a new index, the next term is -0.5. But that means we're taking a positive one on our first partial sum, adding half a value to it. So it goes this plus that. Our new total sum is 0.5. So it went down a little bit. At the third term, we get positive 0.33, but at positive 0.33, we come up here, add the last thing, now it's up to 0.88. Let's do just a few more just to see what can happen. So here's the fourth term of this sequence, -0.25. Here's the fourth partial sum, 0.588. Notice it seems to be actually stabilizing. What's making that work is the fact that this is alternating. Some of the values you're adding are positive, some of them are negative. It's not going upwards the whole time. You took out the -1 to the power n plus 1 part, it's the harmonic series 1 over n, and it actually diverges. This one could converge because we're adding positive terms and then negative terms successively. So on the fifth one, we're at 0.78. And at this stage, let's just see what happens in the long, long run. Looks like it's settling down to something like a 0.69. And the graph on this looks about like that. So an, that's the sequence of partial sum, excuse me, just the sequence itself. So that's in the second column, column B. It's alternating because -1 power n minus 1, but it's getting closer and closer to a value of 0 altogether. So eventually we're either adding or subtracting very small amounts. And this is the partial sum. Started out as a +1, but then it went down to something like a 0.5. But notice, although some of the partial sums are above, some are below, they are converging visually on this graph. What's making it work is it alternates. This is a decreasing sequence, and it has a limit 0. Those are the magic ingredients right here that causes this convergence for the series, that one over here. So kind of wild stuff. And testing this is actually pretty fast too. It's not a long drawn out process like some of the things we've done. What we do is we say, let Bn be equal to 1 over n. So when we go to select Bn, we just ignore the alternating portion, make it the positive portion. I'm using the wrong color coding. Let me reset that. just to make the notes a little bit more readable, let's change it up this way. Let Bn be equal to 1 over n. We know a lot about that as a sequence already. That was the first thing we looked into in section 1.1. We know it's a decreasing sequence because as n gets large, each one of these values gets smaller and smaller. So we can say next, then Bn, this is written as a sequence, is decreasing. We need to say that because that's our first part of the hypothesis of the alternating series test. Next thing we look into is the limit of the positive term. Limit as n goes to infinity of Bn is the limit as n goes to infinity of 1 over n, and it has a limit of 0. We matched that conclusion there. So our work is now done. This tells us, therefore, summation 1 to infinity, negative 1 n minus 1 over n converges. This one deserves an exclamation mark and better penmanship when we fix that up. So this one deserves an exclamation mark, a statement of converges. Let's indicate the test. Alternating series test. Alt is a great shorthand for alternating series test. And if you call this AST, that's a pretty decent shorthand as well. I think a lot of people would know what you're talking about. Be careful with these kinds of big mnemonics, or I'm losing the word on that. Thank you. Be careful with those acronyms. I think I drank too much coffee or something, because sometimes you can come up with an acronym that might refer to multiple tests all at the same time. So just watch out for that. So this converges by the alternating series test. But the other thing we want to say is this series is a little bit special. We have that this one is the harmonic series. Which diverges. This is one series where you don't even have to state a test. If you did, it's really fast. It's just the P series test. But this one right here is the second series that has a name. It goes from n equals 1 to infinity, summation, negative 1 n plus 1 over n. No matter if the index is n plus 1, and minus 1, this affects the total sum, but we call all of them collectively the alternating harmonic series. And the alternating harmonic series, it's a surprise. It doesn't diverge, it converges. So far, these are two series. I think these are the only ones that we're going to come up with the class that have a known name and a known foregone conclusion. But these two come up so often that when they do come up, you can just say the name, alternating harmonic series, converges, and you don't have to do anything further to it. Otherwise, it's just going to feel like busy work to test the same series over and over and over again. Well, any last questions, folks, with part A? Okay, let's try it all out again. And let's take this with us since it's brand new. Actually, we have it on the document, so we can just pull this up as soon as we need it. The alternating series test is right here. Broken down into step 1, we need a decreasing sequence. Into step 2, that sequence has to have a limit of 0, and we get a conclusion of converges. If that breaks right there, no panic, just go right up to test for divergence. That's almost guaranteed to work. Not a full guarantee, but overwhelmingly likely. So let's give this one a try. This is one of those annoying problems where they listed out the terms of the sequence. There are many different kinds of sequences that's going to fit that pattern, but we're going for the most obvious one. So we'll write it down this way as a series going from 1 to infinity of an. Now we need a formula for an. First thing to observe is it's alternating, but I guess we're expecting that, right? But we need to be careful. We can't just put down negative 1 to power of n, because if you plug 1 inside this, you start with negative. So we need to back off by go subtract 1, or you could add plus 1. There's lots of different ways you can go. Let's go in -1. If you put -1 here and plug in n equals 1, you'll have -1 squared, so it does start off as positive. Next thing in this pattern is, notice 2 is just everywhere, so we can just say times 2. But we need something for these denominators. They increase by 2, so we might start with, say, maybe 2n. That helps with the increasing by 2. We plug 1 down in here, we have 2, but we need to be up to 3. So just go +1. That should work. Should is a scary thing to say in these kinds of problems, but this is trial and error, so it's natural to not get it right the first time. Let's take a look. If we plug in a1, this is -1 power 0, so positive, 2, divide by 3. So that works out. We plug in 2 into this formula to get a2. 2 here is -1 power 1, so we just get -2 in the numerator. Below, it's 4 plus 1 for a 5. At this stage, I'd probably be totally convinced, but let's just do one more for the sake of it. A3. That's going to give us a power of 2, so it's a +1 times 2. 3 right here gives us 6 plus 1 for 7. Then double check. We got it. We needed 2 7s, and that's exactly what we have. At this stage, I'm personally totally convinced. The summation is from 1 to infinity, -1 power n minus 1. And here's the positive portion of the series. 2 will go right here, and 2n, I don't think we need parentheses, 2n plus 1. So that's our first step. Kind of annoying. We had to re-engineer what this format was, the nth term of the series right here. But once we have that, we can now define a new sequence. We want the portion that is always positive. So we go, let bn equal 2 divide by 2n plus 1. Now we have to check two things. This has to be decreasing, and it has to have a limit of 0. But first on decreasing, the fact that this decreases is no different than why this one decreases. We have a constant in the numerator, and we have something that grows without bound below. That's always going to give us a decreasing sequence. Let's say, then bn as a sequence going from 1 to infinity is decreasing. And we take the limit of that thing, not too different than this limit. We have constant, divide by something growing without bound. Looks like the limit should be 0 as well. Let's write it out. Limit as n goes to infinity, 2 divided by 2n plus 1 is absolutely a limit of 0. But again, we were using these arguments that feels like we were just waving our hands at it. If you want something a little bit more as a procedure, what you would do is always go into the denominator. We have n power 1, the most dominant thing in that denominator, and just divide everything by n. So this is us not taking the shortcut. You get limit, n goes to infinity, 2 over n, 2 plus 1 over n. But as n goes to infinity, again, much like how this one went to a 0 in the limit, 2 over n will go to a 0, 1 over n will go to a 0. Good thing that 2 survives. That means it's not indeterminate. And this is effectively 0 divided by 2 for a value of 0. You don't have to show this step each time, but if it sometimes helps just visualize how the limit goes, not a bad step to take. This is the shortcut we often take, however. So let's take a look here. It was decreasing, the limit is 0. What does the test say? It says the series must converge. Notice we threw a -1 to a power on it. That means we're talking about the total series now. So here's our conclusion. 3 little dots for a triangle is just a fancy way to say therefore. We deserve a therefore. We did a lot of work. Therefore, summation an, which is as we go from 1 to infinity, -1 power n minus 1 times 2, divided by 2n plus 1, converges by the alternating series test. So that's 2 down so far. It's a pretty fast test, but it obviously kind of doubles the work if you have to come up with the actual formula for your series. Any questions whatsoever, folks, with those two? Okay, let's try out one more, and then we're going to switch gears to a new topic, potentially. We'll see where time takes us. So on this new one on part C, nice that they just gave us everything we need to start out. We have that's definitely alternating, so the alternating series test applies. And we grab this portion, the non-alternating side of it. So let Bn be equal to 2 to the n 4n minus 3. Now, when you look at that, there might be some problems this time. We've been looking at sequences Bn that look like this one. In part B, where the red dot is, that one is obviously decreasing only because n is not in the numerator. We have 2 being divided by larger and larger and larger values in our denominator. That will always be decreasing. This one's a little bit more vague. We have 2n divided by 4n minus 3. I'm not even sure if this is decreasing at all. In fact, something else has gone even more wrong. If you're not sure it's decreasing, what you want to do is go to this part of the test right away. Take the limit of it and just see what you get. Because who cares about getting stuck on increasing and decreasing if the limit isn't even 0 in the first place? There's no need to go investigate all that effort. So let's take the limit of this thing, limit as n goes to infinity of 2 to the n, 4n minus 3. This one's a rational function with the same degree in the numerator and the denominator. And so the output to this limit is 2/4, which is 1/2. Problematically, that's not 0, which implies the alternating series test fails. Again, we're not saying the test is wrong, that someone made a mistake when they proved it, but what we mean is this test only has one conclusion. Its only conclusion is convergence and nothing else. But sometimes you can have a series that alternates and does not converge. Looks like that's what we're dealing with on this one. So if the alternating series test fails, we have to pick a different test. But that's what we were saying at the start of these notes. If your alternating series test fails in this kind of way, go for the test for divergence. That's the next most natural choice. In the test for divergence, we're looking for a number not equal to 0, or just the fact that the limit may not exist. This is where we are actually on. The limit of the entire nth term of this series full on doesn't exist at all. We just need to write that out. Let's say next, test for divergence. Sometimes it's not a bad strategy just to say the test you're using. Now there's no chances of forgetting. We're definitely going to use this test. We take the entire term here, limit as n goes to infinity, -1 to the n times 2 to the n divided by, don't like that times after all, let me write it down this way, divided by 4n minus 3. What can we say about this limit? Well, when it looks like this, the limit's 1/2. Put something alternating in there, and now this limit is going in 2 directions. Some of them are going towards positive 1/2. Other terms are going towards negative 1/2. This is a full-on DNE, which is shorthand for does not exist. That means our work is done. Let's take just another look at this because we've never used the test for divergence in this land just yet. If the limit does not exist, that's our situation. We have a conclusion of divergence. And that's the only conclusion test for divergence could give. So we'll just say down here, the series diverges. And our work is complete. This is something that happens a lot in the homework. I think about half of the alternating series are going to converge, the other half are going to diverge. When they do, and you grab the positive portion of the series, and you get a limit non-zero, this is the next thing you can say. The total limit with the alternating part cannot exist if you get a non-zero value right here. Well, any questions at all, folks? What, getting through part C? Okay, so that's the alternating series test. We're starting to collect a lot of tests at this moment. And here is where my earlier comments about these tests being interconnected start to actually come into play. We actually have a literal type of trichotomy that's going on here. And this comes from our new definition of what we say by absolutely convergent. So a generic series is said to be absolutely convergent if the series, where we take all the terms and place an absolute value on them, converges. This is actually kind of tough notationally, so let's write down something above. Summation n goes from 1 to infinity, absolute value an is not the same, is not equal to absolute value n equals from 1 to infinity, summation an. So that's one thing we have to think about immediately when you're looking at this right here, where there's an absolute value on the nth term of the series. The reason these are not equal is because over here on this red dot, this is equal to the absolute value of A1 plus A2 plus A3 plus, and so on. And you cannot break up absolute value across pluses like this, not without getting an equality. On this one, just sort of insert some space here. On this one right over here, summation is we go from 1 to infinity, absolute value an. This is saying take the absolute value of A1 plus the absolute value of A2 plus the absolute value of A3 plus, and so on. So these quantities, when you're taking absolute values individually versus over here, they're totally different. And thinking in terms of order of operations, that kind of makes sense. Even though this is an infinite sum, you would expect by order of operations, you have to find the sum, then take its absolute value. Over here, you're finding the sum of the absolute value of all the terms individually. So watch out for that. That can cause some weird logical problems whenever you're thinking of this, but looking at that, they're not the same. So the great thing about absolute convergence is that if the series an converges, but this absolute value of all the terms diverges, we get a new concept called conditional convergence. Conditional convergence means, well, your series converged on the condition you didn't slap absolute value on every single term. A very, very typical series for conditional convergence is this one. Summation n goes from 1 to infinity, negative 1 power of n over n is the convergent alternating harmonic series. But what happens to it when you do this? You would get a different series for sure, and it would look like this. Summation n goes from 1 to infinity. So if we're trying to match up this form, the absolute values go inside like that. Negative 1 to n, divide by n, summation as n goes from 1 to infinity of 1 over n, but now this is the divergent harmonic series. Sorry, I should have left a little bit of space between here in the notes for folks that might have printed these out. But what this is all now saying is, therefore, summation as n goes from 1 to infinity, negative 1 power n over n, the alternating harmonic series, in other words, is conditionally convergent. It's convergent, in other words, on the condition you allow the terms to actually alternate. Take the absolute value of all the terms, and now it's a divergent series in total. Absolute convergence test says, if the series does converge absolutely by putting absolute values on it, then that series is convergent in fact. So that's kind of fun, but it doesn't work for conditionally convergent series. And this is what makes way to the trichotomy. Any series you write down, every single one fits into exactly one category. It never overlaps. Your series is either going to converge absolutely. That means you can slap an absolute value on and still get convergence on it. And this test then says the original series had to converge in the first place. Or it can converge conditionally. That's what this hat does, the alternating harmonic series. And the last thing that could happen is it could diverge totally. So only one of those three things can happen. And that's what we're going to resolve in example 3. These problems are a little bit longer. So when you go to do them in the homework, I'd say this section of the notes is a good place to come back to. I took a look at the ones I assigned, and I made just small changes on some of these because they're hard enough. This is more of a guide from the homework at this point to help out. These are a lot longer problems, so we're definitely not going to attempt it, but this is us getting started, seeing how the material goes. When we come back Thursday, we're going to refresh this and give these problems a try. This might actually take a good amount of class, but we'll use the rest of our time to take a look into section 11.6. Well, any last questions or comments, folks, before we call it a night? Okay, well, have a great evening, everyone. We'll reconvene Thursday and just get right back to it. More series and sequences. You bet. Have a good one, Rhett.